All right. So, hello everybody. My name is Guillaume Morin. I work for PCI Geomatics. I'm not going to tell you the full title of the presentation because I'm going to run out of breath. Basically, what it is we had a customer that was interested in doing ARD work to monitor assets, which is a forestry. So that customer is PFC, for Pacific Forestry Center. They basically monitor forests across Canada. We're going to talk about them a little bit so you understand what they do. We're going to describe the system we set up for them so they can do the analysis, what we learned from that, and then we're going to talk quickly about what we're thinking doing in terms of ARD product and Open Data Cube development, and a few slides and nice to look at slides and a few conclusions. So with the PFC, basically there's a 145 years old institution. They're one of the 5 biggest forestry monitoring institutions out there. And they are doing forest monitoring and climate change detection. From a NEO standpoint, they do many other things, but the things we look at from a NEO standpoint is those two, forest monitoring and climate change. To give you some context, basically over the last 40 years, Canada, where I came from, lost about 1% of its total forest. Gone. I mean, that's about 45 million hectares. If you look at the other side of the diagram, basically says that every year you lose about 5% to insects, 0.5% to fire, 0.5% to lumber, and then the things that you really lost is 0.2% to actually converting to something else. So, we know that because PFC have done the science and they looked it up. And how they're doing it is basically they have this grid of sample points. They look across Canada, and for each of the little square, they look at what changed from one year to the other one year. And they pay people to basically look at those little squares and draw pixel around it. Well, sorry, vectors, and they derive product, which is very valuable. But as you can imagine, it's quite intensive work-wise. To give you a little bit of an idea what the scale of it is, this little red box is a Landsat 7 image. Give you a sense of the scale of what's going on there. So quite a lot of little boxes you need to check. So that's a process that works, but obviously has problems. So first of all, as you see, they're looking at little squares as samples because they cannot do the full data, just too much data. It's need a lot of manual work. They need to remove the cloud. They need to look at those squares. So they have the rules. Basically, they cannot use 2 scenes in a square. It has to be from one single take. So you have to kind of scrub around all that data to find the perfect one. And you have to look it up manually and delineate those little pixels. So that's a lot of work. So they come to us and with this problem, and we try to help. So what we did is we designed a little prototype, which is an ARD system, or we like to think it is an ARD system at least, that is composed of boxes. I'm an engineer. I like to think into Lego block. Break down the systems into blocks. So that's what it is. We had the Open Data Cube that let us store that data into an easy to access, easy to manipulate form. We use a COS, a Council First Observation System, portal, which is a nice little user interface you can use to query the data and play with it. And then we use our own in-ground software called GXL, which is basically a distributed processing system to process the data to bring it to the level they needed to do the analysis. And we're going to discuss a little bit about the workflow and the algorithm later on. Okay, so let's talk step back a little bit. And what are the key requirements for time series analysis? You need ARD product. So super registered, remove all the geographic gibberish, and radiometrically normalize. you need the ability to store that data in a single, well, easy to access way. And that's the ODC, Open Data Cube. And you also use, well, tools and algorithm that you can run on that big stack so you can derive information from that data. So, well, I was supposed to go first, so I was going to introduce what the Open Data Cube is, but I got my thunder stolen a little bit. So what is the Data Cube? Well, it's basically a giant repository, or we can store all your Earth observation data. It was created by our good friend at Geoscience, started in 2014, and that morphed into the Open Data Cube. I don't know when that started, last year, 2 years ago? Okay. Yeah. Which basically is open to the world for people to use, and we're very thankful for that. And that lets you basically drill down all the data you have stored in there and extract information. So again, stealing your slides. So that's an example of the thing you can do with the Open Data Cube. You can basically monitor tide and get low tide, high tide, and a nice little, much nicer animation than mine over Australia, for example. Or a very stunning one too is you can monitor where water goes. So to give you a little bit of an idea what's going on, there's rivers that kind of weave over the years, and what you see deep blue is water that's always there, red is rarely flooded plains, and all the color between is basically where the water goes over the years and over the seasons. So really, really cool science you can do with all that. COS, Council for Operation Science, I got it right this time. Basically, they embrace the Data Cube. They say, we know what, we're going to evangelize it, and we're going to make it public, and everybody can use it. And that's really a great initiative. You should check them out. They actually have a very cool demo. You can play with the Data Cube and really see what's going on. And when I saw that, I said, yeah, that's really cool. I want to do the exact same thing for those guys at PFC. So I take all those Legos, went home, and I'm going to build something with it. Oh, no, I forgot about that slide. So right now, there's really 3 working Data Cubes. One in Australia, obviously, one in Switzerland, and one in, I want to say Bolivia, but I might be wrong. Colombia. Oh, Colombia, sorry, guys. And a lot of people looking into it. That's really a hot topic, and for good reason. It's really awesome tech. So when you talk about big data and other things, there's a thing somebody coined the 5 Vs, which is volume. You need to be able to process a lot of data. You need the velocity, being able to process it quick, so you can extract information fast when it's relevant. You need to be able to verify that data. You need to know what happened to that data, so you know somebody didn't fudge the numbers. And you need variety. You don't want to look at one single sensor, because you want different perspectives that give you the insight in there. There's a value, which is, this comes from Adam Lewis' paper, I believe. So he didn't really discuss about the V, but that's our interpretation of value is basically you can leverage all that data to create good science and good insights. So let's talk a little bit about our own stuff, the GXL system, which is basically a high volume mosaicing and platform workflow. It's a distributed processing system that we created. It's designed to handle a large volume of data, both in quantity but in variety. I mean, PCI, we pride ourselves in supporting pretty much every sensor out there, remote sensing, Earth observation system. So we have a lot of experience about supporting multiple sensors. And when you have to support multiple sensors and processing the same way, well, you have to make sure you understand them in a kind of uniform fashion so you can process them easily. The other bit is it's basically a very nice parallel processing platform, ideal for prototyping stuff. I might be biased in that because I designed the system, so I kind of know it pretty well. But I tell you guys, it's a great system. So that's great. So we have the data cubes there, we have the COS at Gilbert, and the GXL that process that data. So how do you go from point A to point B or C? Well, you process the data in the GXL using little processing that we're going to discuss what is an ARD product. So you do that magically. And then for those familiar with the ODCs, they basically require metadata. So they take a file and metadata, and you need to populate that so you can use the data. You know, when the data was acquired, what is the car coverage, where the bad data is, all that stuff. And then you basically go into Open Data Cube land, and you trigger an indexing and ingestion of the data if you need to transform it a little bit. So that's what our prototype did. Sometimes with a little bit of glue, but overall it worked pretty much automatically. So let's talk a little bit about ARD product and what we think is ARD. So when we were on a little group talk, people were saying, well, it's n-1 to what I do. So it's not one single ARD product, but it's, you know, as far as you want it to be and how you need it to be. So we have kind of two little workflows we created. One is for Landsat 8, doing vegetation monitoring. And so, you know, you do basically ingestion, pan sharpening. I know that's a dirty word in some people's mind, but we'll talk about that later. Solar azimuth correction and zenith. GN to reflectance. We talk about physical property, spectral classification, BRDF correction, topographic normalization, typal SCAP, spectral indices, and then you load that data into the data cube, and you have a data that is ready to be analyzed by people that know what they're doing. Another case, using Sentinel-2 and, you know, doing forest monitoring. So it's not the same application, so it's not going to be the same process. Again, ingest, pan sharpened, spectral classification, weak registers, because sometimes Sentinel-2, especially when there's a lot of cloud, it's shifting a little bit, so you need to kind of make sure those pixels are straight. Radiance, because they develop the production of reflectance, you know, radiance, reflectance, you have to jungle with that. Atmospheric correction to remove all those spacey cloud and all those haze you don't like. And again, I'm not going to go over it, but you get the idea, right? It's a modular approach. You have to be able to load those algorithms in there to get the product you want. So yeah, let's take a little bit about the pan sharpening, which is, as I said, a dirty word. So pan sharpening has been around forever, but there's a lot of people critiquing it because it's affecting the spectral information in the data. We believe we have a new technique that is much better than the previous one. And my colleague will present that ad nauseum later on. I'm just going to brush over it very quickly. So this is Sentinel data, basically. And what we did is we created all the bands and bringing them to 10 meters and preserving the spectral information. And that's, you know, I don't know, I like working with that data more than this one as a face of it. And as long as the spectral information is preserved, obviously. Otherwise, it's just garbage. It's made up data. But that's not what it is. At least we believe, well, we think so. Another thing that is important for ARD is making sure your pixels are in the same place. And those two scenes on the same area, one with very little clouds, another one with a lot of clouds. And as I said, that goes some problem into the Sentinel processing chain. So a few sites we're going to look at. Basically, you see there's a bit of misalignment in between the scenes. And we're not talking about subpixel there. It's like good solid 2-pixel misalignment in there. So we have some tools that let us kind of magically fix that. Yeah, and that's very important. And pixel precision is not enough. You need to go subpixel. Because subtle change is going to introduce so much noise later on in your analysis. Well, okay, depending on what you're doing. Sometimes subpixel is very important. So again, we're going to go back to this little kind of pillar thing. And this is how we see we fit in that little thing. Is we know how to process pixels. We know how to make your data kind of up to the level you need. We're not going to go into storing the data as this problem, as far as we're concerned, is being solved by other people. The Open Data Cube does that very well. And for the multi-temporal analysis, well, we think we can bring some analysis tools with some very good science out there. Geoscience Australia have some very, very cool algorithms that are available on GitHub. I've used them. So basically, I'm putting those names because I've used those algorithms. I've used NDVI anomaly from CEOS that was part of the little demo tool. I've used geomedian to get nice mosaics, well, composites, sorry, out of it, and I've used some of our tools to get really all the information PFC needed. So, that's a cool project. So I think I didn't mention what I've used, but I've used Landsat 8 and Sentinel-2 data for a little area in northern, where was that already? Alberta, sorry. So what did we learn? Well, using existing open data cube algorithms such as CEOS and Geosortation from different sources is difficult. I mean, I spend weeks and weeks and weeks fighting with metadata issue, band naming, no data projection, and so on. I mean, for example, one person going to name in their metadata band red, the other one going to name it B01. So yeah, I don't care. I mean, that's fine by me. And then I ingest all that data in there, and I was good. Everything was working fine. And then I tried to run my NDVI anomaly, and I got an error saying, well, where's my red band? I don't know. It's there. You look at the spectral information. So band naming. No data value. I was 2-sensor, Landsat 8, and Sentinel-2. I did it quick, and I set the no data value to be 0 for one, and minus 999 for none. And I run it, say, oh, no, has to be the same values. So all kind of thing like that. It's you have to make sure that you basically have to know the algorithm. If you want to ingest the data and use existing algorithm, you have to know the algorithms, what they're going to do with the data, so you can use them. I thought naively that, yeah, I can run it. It's in data cube, everything's going to work fine. Yeah, not quite. And yeah, leveraging multiple sensor is quite hard at the moment. I mean, it worked great for Landsat. Everything works perfectly for Landsat. It's great. Trying to use Sentinel-2, it's a little bit of another story. You need to read 3 different formats, and you have to modify scripts and hope it works. And then you understand that, well, Sentinel-2 has near and near-wide. Which one do you use to compare it with Landsat? All those kind of little pesky things. That's kind of hard. I'm going to go back to projection because I thought it was pretty clever. So in Canada, we're a pretty big country, like the US. But so when we've been given data in UTM zone, well, there's a good chance that the area is actually spanning to 2 UTM zones. So that's not good for us. So I thought it was pretty clever. So I'm going to use LCC for Lambert conic conformal. So, well, first of all, it was not supported at the time of the data cube. Say, okay, I can roll up my sleeve, look into the code, added the projection, and then I wanted to use the algorithm that was listed before by CEOS. Turns out, well, they use a geographic. They didn't want to know anything out of data I loaded, so I had to go back to the drawing board and try it again. So what I'm trying to get at there is we need standards. You need to have something that is somewhat, an RD product should be a minimum set of things in a certain way. So you don't have to, once you get that, people are going to start creating the algorithm to use that standard. You don't have to kind of know the algorithm before you can ingest the data. That's one of the key things I learned. We need to be able to deal with multi-resolution sensor. I mean, Landsat is 30 meters, or 15 if you pan sharpen it. And Sentinel is 10. I mean, that's a big discrepancy. And if you want to increase the temporal frequency of your data and use them as interchangeable, you need to be able to work on a similar kind of resolution because you want to compare something that is comparable. And that one, the last one is, yeah, you need to be able to have some kind of a framework for MTA so you don't run into the problem I run into and say, oh yeah, you need the red band, but what is red? I mean, nobody knows what red is or blue is for that matter, or near. I mean, it's different for each sensor. So the algorithm should not be asking for red, it should be searching for something else. So maybe, and that question is I realize a big can of worm, but that's why we're all here, to sort it out. Okay, so let's talk a little bit about what we've done and what we're going to do in the next future. So we're going to do, that little chain there? It was kind of a white lie, because at the time when I created the prototype, we didn't have it. It was all manual steps I had to run one after the other. So we're going to make sure that everything is run from point A to point D automatically. You don't have to touch it. OBIA, object-based image analysis for MTA, because right now we're looking at pixels, 1 pixel at a time, and we were doing that in the. I'm not old enough. In the 90s, I guess that's what we were doing with satellite data, 1 pixel at a time, and then came the object-based analysis. So I think there's something for multi-temporal analysis and object-based. We want to add SAR. I mean, that works, but I'm sure there's other things you can do to get ARD for SAR. And of course, we want, we pride ourselves, as I said, in using multiple sensors all the time. And I think we want to add more and more sensor in an easy way, not something that takes you a week for the engineer to kind of come up and understand what the format is and the 3 different formats for Sentinel 2. No, I'm not Peter, I tell you. So yeah, that's what I think, we're going to work on. So kind of nice slides. So that's a little result what we did. So this is over Fort McMurray in Alberta. That's the OpenCR data cube. So they have a very nice interface. You can draw a polygon, and you can do an NDVI anomaly. And what you see is those things popping up. And we show that to PFC. They're all excited about it. So, oh, that's great. This is actually looking at it. It's a pre-clear area. So they were immediately being able to derive science from that, and really kind of digging into that and really exploring the data in a different way. And that was really, really exciting to see them go. So another thing is when you do composite, there's different techniques. You can use a mean or max NDVI depending on what you're looking for. But you see you get all kind of weird artifacts in the waters and stuff in bright soil. You get some weird stuff. And so we got to play with geometric median, which is a great tool. I mean, props up to Geostory. We want to use that more because that's really, really cool tool. Oh, here you go. So one of the take we did, so you are talking about multi-resolution. You get the 2 seat. So how do you deal with object-based and multi-resolution data? So this is, what you're looking at is 2 synthetic image. Is it? Okay, I can't see. Let me see, is it on 2 slide? Oh yeah. So that's basically what we did is we created a synthetic image using Landsat and Sentinel using objects. And as you can see, there are very similar features. And now you can compare stuff because one is you can compare the same object with the same object. Another one, there we go, Landsat 8. Okay, so let's talk about what it means for PFC a little bit. Because there's the customers, there's the one that matters. There's the one that needed problem solving. So they were able with the system to, over a small area because it's a prototype, but still, able to do a systematic coverage and data extraction. So that's big data. And that lets them do better science because they don't have to rely on samples and stuff. They can actually look at the entirety of the data set, of the data. It can be more accurate. They can use better resolution because they can use 10 meters instead of the 30 meters. And they can use more sensor. Landsat, Sentinel, Planet, you name them. So if we go back to the what it means, those 5E for PFC, well, they're going to be able to analyze all counter forests, no more sampling. We're not there yet, but that's the goal, right? With the data cube, they're going to be able to reduce the lead time between the measurement and the decision making, or at least the results. You don't have to do all the manual process, it can be done automatically. All the metadata is going to be populated so you can make sure that you understand what has been done to the data to come up to that answer. And if something goes wrong, you can go back and reprocess it. They can use medium, high, and very high resolution data. So that's something without added cost. Little added cost. And finally, I think what's the value for the customer? That's what I think is what's important is better measurement, means better accountability, it means better governance, right? That's what is important. You're able to affect the world in a good way using remote sensing. That's why I'm in the business, is to make a difference and I think those kind of tools let you do that. That's it for me. You have time for questions?
Probably for one question. Any pressing question, thoughts?
Did you do a question? Oh,
Yes.
what?
Greg.
You mentioned earlier about normalization of radiometric processes. How do you plan to do that in your upcoming work? Is that spectral response curve-based or some other methodology?
As I say, I'm an engineer and a scientist. I mean, that's a question for somebody that is not in the room, unfortunately. I can come up with an answer for you later on. I really don't have the answer. I'm sorry.
Thank you.
Any other questions?
So one of your points was to move forward, we needed some algorithmic basis for defining our analysis. What do you think?
Well, what I'm saying is right now it's a bit of a free-for-all. As I said, when people design the algorithm for the Open Data Cube and multiple MTAs, they say, oh, you need band red and you need in long lat. And the next guys are going to come up with another algorithm and say, well, no, I don't use landlat, I use some kind of other projection, and I'm going to use the wavelength or the band number. And that, I mean, it's okay, it works for their particular case, but if I want to mash them up together, that's a giant pain. So that's what I'm trying to say is, if you have kind of a common way of accessing data, this problem should at least be not disappear, but minimize, right? You want to be able to, I mean, that's what's the beauty of open source. You can take the stuff and build up your kind of big giant chain and get a result at the end. But if everybody kind of talk of a different language and use different, I'm going to put it, conventions, that kind of defeats the purposes because you have to spend a lot of time rewriting all that code. And I think that having standards in ARD going to drive that because now you're going to look at one single kind of container and everybody understand what it is.
So is another way to say that if we had some common way of talking about the analytics that we want to perform on how we prepare the data, how we do ARD, that would be helpful. If you knew how you were going to analyze the data, it would help you prepare the data.
Yes, and the other way around too.
Okay.
If the data is always in the same form, everybody going to analyze it in the same way. I mean, they all access it in the same way, which means you could be able to kind of, yeah, at least that's what I'm saying. I'm not sure it's realistic, but that's what I'm hoping we're going to be able to achieve in those 3 days, or at least start the process.
Cool. Thank you again.